Good day everyone, we are Motus Fanaticus and we are here today to present the 3 demonstration for our chosen concept.
Have you ever wondered how a simple candle flame can be used to power a fan?
Demonstration 1. Heat transfer.
For demonstration 1, the things that we need are 2 metal spoons, cold and hot water, 2 cups, an infrared thermometer. This demonstration is to show how heat transfer flows from hot to cold, which is an essential for understanding the Stirling engine's hot and cold reservoir. We place 1 metal spoon in each water, hot and cold cup. Then let us leave them for a few minutes. After leaving them for a few minutes, the temperature of the water is now transferred to the metal spoons.
After the switching of the spoon, the hot water became lukewarm while the cold water gradually warmed up. This process is a practical example of the second law of thermodynamics. This is a simple manifestation of thermodynamic principles that govern all heat exchanges. This principle is used in engines like Stirling Engine, which operates by transferring heat between 2 reservoirs, one hot and one cold. In this case, the spoon serves as a medium for heat transfer.
Demonstration 2. Expansion and contraction. The materials needed are balloon, 2 containers, hot and cold water, and plastic bottle.
I will demonstrate how expansion and contraction of a balloon works using hot and cold water. So I will put this balloon with no air on a hot water first. Cold what? Hot water. Now cold water. Ta-da-ding. Further explain why this balloon expands when it is put in hot water and decreases in size when it put in cold water, simply because the hot water moves the air molecule faster and spread out, while in this cold water, the air molecules started to get together and slow down.
On the other hand, when the gas in the Stirling engine is heated, the particles also gain kinetic energy, causing them to move faster and spread out, which makes the gas expand. This expansion forces the piston to move, generating mechanical work. As the gas shifts to the colder side of the engine, it loses kinetic energy, causing the particles to slow down and come closer together, resulting in the gas contracting. This contraction creates a pressure difference that pulls the piston back down. Demonstration 3. Stirling engine. The materials needed here are couplings, stainless rod, CDs, used cans, balloons, sandpaper, rubber bands, popsicle sticks, candles, screws, bottle cap, steel wool, and tools.
Think about a hot cup of coffee cooling down. The heat escapes into the air, just like in the Stirling engine, where heat flows between the hot and cold sections to keep the cycle running. Or picture a balloon. It inflates when warm air expands and deflates as the air cools. That's Charles' law in action. And it's the same principle driving the expansion and contraction process in the Stirling engine.
Now that we've seen Charles Law explain the Stirling engine motion, let's take a moment to explore an exciting question. Why does this concept matter? It's not just a cool scientific model. This knowledge helps us power our world in ways you may not even realize.
Let's start with solar power generation, one of the most promising uses of Stirling engines. Imagine a bright, sunny day where massive solar concentrators collect and focus sunlight onto a single point. A Stirling engine at the focal point converts the intense heat into mechanical energy, which is then transformed into electricity. Next, let's shift gears, literally, to automotive engines. While not all cars use Stirling engines directly, the principles are foundational. Car engines convert fuel into mechanical energy that powers the wheels. Just like the Stirling engine, they rely on precise heat and motion control to turn energy into movement, enabling the vehicles we use every day.
Now, take a dive into the mysterious world of submarine propulsion. Submarines need quiet, efficient engines for stealth and endurance underwater. Stirling engines are ideal here because they can operate with minimal noise while providing the power needed for long, deep voyage.
And up in the skies, the same principles play a crucial role in aircraft engines. These engines, also known as aero engines, convert energy from fuel into the mechanical force or thrust that allows aircraft to take off, climb, and fly. Understanding how heat and motion interact is essential for keeping us connected to the world above.
Welcome to the demonstration of a Stirling engine model. But before we dive into the engine in action, let us first explore the different parts of engine that comes together to create the mesmerizing rotational motion.
First up, we have the cylinder, a critical component of the engine. Inside, you'll find the displacer made of steel wool. This clever material isn't just any filler. It's porous, letting air flow freely while providing a large surface area for heat exchange. Its movement transfers heat between the hot and cold sections of the cylinder, keeping the cycle running. Next, the power piston. Crafted from an elbow pipe, a soda can, and a balloon. The soda can houses the working fluid, essentially the air inside. The elbow pipe connects the cylinder to the displacer, and the balloon acts as a flexible seal, keeping everything airtight and ensuring smooth operation. Simple yet effective. Next, we have the metal rods. These rods form the crankshaft, which translates the linear motion of the displacer and the power piston into rotational motion. They also allow the displacer to move up and down seamlessly within the cylinder, ensuring a smooth cycle every time. And lastly, the flywheel. Once everything is working together, the flywheel showcases the engine's output by converting the crankshaft's motion into a smooth, continuous rotational movement. It's a simple yet elegant way to see thermodynamics in action. But before we start working with the engine, here are the few things to consider during the demonstration, which includes the proper sealing, fire safety, and heat.
Ready to see it come to life? Let's light this candle and put it in motion.
Watching the Stirling engine model in action, you might find yourself asking, what's the magic behind this marvel? Actually, let's rephrase that. It's not magic, it's physics.
So what exactly is the physics driving this engine? To break it down and truly understand the science, keep these 4 key concepts in mind. The first law of thermodynamics. First law of thermodynamics tells us that energy cannot be created or destroyed, only transferred or transformed. The Stirling engine demonstrates this beautiful by transforming heat energy into mechanical work. Heat from a source, such as a flame, is absorbed by the engine's working fluid. This energy causes the fluid to expand and push against a piston, performing work. Some of the heat is then transferred to a cooler area, completing the cycle. The second law of thermodynamics. The second law of thermodynamics states that heat flows spontaneously from a hotter object to a colder one. In the Stirling engine, this principle is at work as heat moves from the hot source to the cold sink. The Stirling cycle. The Stirling cycle consists of four main thermodynamic processes: the isothermal expansion, constant volume cooling, isothermal compression, and constant volume heating. Step 1. Isothermal expansion. First, heat from the hot source causes the working fluid to expand at a constant temperature. This expansion pushes the piston outward, performing work. This is where Charles' law comes in. When a gas is heated, its volume increases. Step 2. Constant volume cooling. Next, the fluid is moved to the cold sink, where it cools down at constant volume. This reduces its pressure and prepares it for compression. Step 3. Isothermal compression. In the third phase, the cooler working fluid is compressed at a constant temperature. The piston does work on the fluid, and heat is released to the cold sink. Step 4. Constant volume heating. Finally, the fluid is returned to the hot region, where it absorbs heat at constant volume. Its pressure increases, setting the stage for another cycle of expansion.
Why does understanding thermodynamics matter? Because it gives us the tools to harness energy in innovative, efficient ways, whether it's powering our homes with solar energy, exploring the depths of the ocean, or connecting people through flight. These principles are the heartbeat of progress.
And it all starts with the simple ideas, like how heat makes air expand or contract. Concept we saw at work in our Stirling Engine model today. By learning how energy flows and transforms, we unlock a world of possibilities for building a better future.
As we wrap up, let's take a moment to appreciate the beauty of what we've explored today. The Stirling Engine isn't just a mechanical marvel, it's a gateway to understanding how energy shapes our world.
From the heat of the sun to the depth of the ocean, and from powering machines to enabling flight, these principles drive the innovation that fuels our future. But the real magic lies in how such simple concepts like heat, motion, and expansions comes together to create something so powerful.
Thank you for joining us on this journey into the science of the Stirling engine. I hope it's inspired you to look at the world a little differently and maybe even spark your curiosity to explore further. Remember, the possibilities are endless when we understand the energy all around us.
Grabe naman! 99 sa physics.